Hello, this is Mr. Manley. I'm going to do a quick video to show an example of a method of math induction. I'm not going to go into the background or the concept. I'm just going to go straight into the example. Here we're given this series that follows a particular pattern, and it's suggested that the sum of this series is equal to this expression, and we want to prove that this is true by a method of math induction. So it's a three-step process. If you're using the text that I use with my class, it actually looks like a two-step process, but I talk about it as a three-step process. And the three steps are always going to be, one, we're going to show that this is true for n equals 1. 2, we are going to assume that it is true for n equals k, which is an assumption that we accept because we could let k equals 1 after we show that it's true in the first step for n equals 1. And then finally, the proof will be completed by demonstrating that this is true for n equals k plus 1. And then that will provide the domino effect that transfers to all cases. So beginning with step 1 here, we're just saying that when n equals 1, and we can see, first of all, we can see n equals 1 here. So there's n equals 1 right there. But I also want to think about, where did that come from? That came from letting n equal 1 here. So either way, n equals 1 is 1/2. And then I want to show that the sum of the first n terms is equal to this n over n plus 1. So now I plug in the n here to that expression. So hopefully that's not confusing. I plugged it into this expression, which had really already been done there, so didn't need to do that, but that's what's happening. And then I'm plugging it in here and showing that these are going to be equal. So plugging in a 1 onto the right side, I get 1 over 1 plus 1, which is in fact 1/2. So 1/2 equals 1/2, and this is true. This statement that we're given is true for n equals 1. Second, I'm going to assume true for n equals k. And the way that I'm going to show that is by plugging in a k for n in the expression. This is the n equals k step. And that's all we do. We just plug in a k for n. And then the third step is to demonstrate that this is true for n equals k plus 1. And in this type, when I write this out, when it's a series, and this is just a common way of practicing math induction, is through proving a series. And in this type, I'm going to write out the k term. So this is the series. I'm going to write out the series up to k. So there's the series up to n equals k. And then I'm going to go one more to k plus 1, which would be k plus 1 times k plus 2. You see that? If I take this k plus 1 and I plug that in for n, I'm going to have k plus 1 times k plus 2. And we want to prove or demonstrate that that is equal to letting n equal k plus 1 here. So we're going to put in a k plus 1 there. That's going to give us k plus 1 over k plus 2. And then the method, almost especially in these series types of problems, the method always involves recognizing that this piece here is in this piece here. So I have a match there, and because I have that match, I can make this substitution. You see that? That series up to 1 over k times k plus 1 is replicated, so I can make the substitution k over k plus 1. And this will always be the case in this type of series. So it's k over k plus 1 is substituted, and then I just have that piece. I still have that. So we're going to add that. And that's here. And now the remaining work here is to take and show that this is in fact equal to this. Okay. So I'm going to get to another page here. And I'm just going to, essentially what I'm doing is simplifying this, right? All right, so I've got k plus 1 over k plus 2. Is that what we're trying to do? Let's take a look. Yeah, so that's what we're trying to do. K plus 1 over k plus 2, and on that other page I showed that this is equal to that, so that's a check and the proof is complete.